Alright, so you're starting with iron sulfide or pyrite, oxygen gas, which, when added together and reacted, yields iron 3 oxide, aka rust, and sulfur dioxide, which is a trash gas, but that doesn't really matter. Now, in this, you are reacting with a limited amount of pyrite, and you have a plentiful oxygen, so you don't need to calculate anything with oxygen. Now, iron oxide, you have elemental iron, so is FeS, is what the compound is. You add that to oxygen gas, which is O2. This yields iron 2, oxygen 3, plus SO2. So you get iron sulfide plus oxygen gas yields iron oxide and sulfur dioxide. From that, you have to balance the equation. So you rewrite that. Now, I will normally write what the phase of the element is in case you need it. Let's SO2. Okay. Oh. Alright. So you're starting off with the iron, the oxygen, which goes into the rust and gas, the sulfur dioxide. So what happens is you have to figure out, this is balancing the equation though, by the way. You have to figure out how to get the same amount of this on this side and the same amount of this on this side. So you have the same amount of iron on this side so however amount of iron is on this side has to come out on this side. How many amount of oxygen has to come out on this side. However much sulfur also has to come out on this side. But you also have to be able to take those numbers and make them back into this. So in this, in the base equation, you have 1 iron, 1 sulfur, 1 oxygen on this side. 2 oxygens, sorry. On this side, you have 2 iron with 3 oxygens plus 1 sulfur and 2 oxygens. And these dashes is for the amount of moles of these you need to react. So what happens is, in this equation, you need 4 iron sulfide, which gives you 4 irons and 4 sulfurs, plus 7 oxygen dioxygen, so O2s. So that gives you 14 oxygen atoms to work with. This turns into 2 iron oxide because you use up all 4 of the irons because it's 2 irons in the compound, and you use up 6 of the oxygens because it's O3. This also gives you 4 sulfur dioxide because you're using up all 4 sulfurs and the remaining oxygen. Now, when you go to, let's see, what was B? The amount of fool's gold in the sample, the iron sulfide. This is how I was taught, because I normally converted everything to grams before I worked with it. So I would take the 5.250 kilograms and convert it to grams, which is 5,250 grams, if I can write correctly. Apologies if this is sloppy. My brain works faster than my hand. So now you have 5,250 grams of the rock. So I'm going to label that just because I saw that you need labels. And on top of that, this is 4 significant figures, because this is where that'll start coming into play. So, and just to be safe, because I don't know how critical your teacher is on it, normally you don't worry about significant figures until the very end. but not knowing how your teacher is, and I don't know how they teach it up in Canada, they might want you to round for the significant figures with each step of the equation. So this is for significant figures because you will have, sorry if I'm pointing to the wrong part, 1, 2, 3, 4. Yeah, 1, 2, 3, 4. And the last one is the uncertain digit. That is the one that you would always round if there's further ones past it. So from that, you would take 5,250 grams, multiply that by 0.4355, which is the 43.55% of the fool's gold in the rock. And you get 2,286.375 grams of iron sulfide. Now, if you need to round this for the significant figures, you would then be working with 2,286 grams of FeS. You would cut off, so then you work all that, but if you need only 4 significant figures, you would go with this one, because you would cut off what's left past the decimal, because this is only 4 significant figures. You have your 3 certain and 1 uncertain, which is the one that rounds at the end. Sorry if that's not... There it goes. Now that you have the amount of iron sulfide, and you have a balanced equation, you can figure out how much the theoretical yield is, which is C. Actually, let me label this real quickly, just in case you pause the video and need to just look at it. So, the grams of iron oxide that can be theoretically produced. This is how much if you have a perfect reaction. Nothing goes wrong. That never happens. At least in lab work or anything like that. Maybe if you have machines doing it, it works, but we're not going to get into that. So you're starting off, and I'm going to do it with, I'll do both with the 4 significant figures and without it, just in case you know how much it, well, what your teacher wants, hopefully. So if you're starting off with 0.375 grams of FeS, or, okay, you multiply that by 1 mole of FeS over the grams per mole weight, which is the combined weight of the elements. So iron is... Alright, I know sulfur off the top of my head is 32.02 grams per mole. That is the weight that is on the periodic table. You add that with iron, and you have the full weight of the compound. So you divide, it's kind of like a fraction, but don't think of it that way because you might actually confuse yourself. So you'll understand it probably a little better when I show you in a second. FeS. So what happens is, this is how you're starting off the equation. You have the iron, iron sulfide, and you're multiplying it by, oh, come on, focus. There it goes. Iron sulfide, multiplying that by 1 mole. Oh wait, is this... No, it's not. 1 mole of the iron sulfide divided by the molecule weight, or the gram per mole weight. The atomic mass, sorry. So then you would multiply that by the amount of moles in here. So what happens is that there are, and you have to cancel everything so that you can get to the iron oxide. It is very, very similar to basic algebra if you're just working with units. So what happens is that you have the iron sulfide, which gets multiplied by the 2 moles Fe2O3 divided by 4 moles FeS, because what happens is that up here, sorry about that, my phone went off. up here you have alright, here's iron sulfide. You have 4 iron sulfide, which is what you divide by because you're canceling out iron sulfide. It cancels downwards. And then up here you have 2 iron oxide, which is what you have on the top part because you're trying to get that across the equation, because that's what you're ending with. Which then you multiply again by the atomic mass of the oxygen, not oxygen, iron oxide, which is 159.69 grams per mole, because that's 3 oxygens, which is 48, plus the 2 iron, which, again, sorry, I can't think of that off the top of my head. You divide that by 1 because it's 1 mole total of the iron oxide. So 1 mole of iron oxide. This equals, alright, let me show you that again, right there. So then, when you're crossing, because then you're canceling out moles. Yeah, correct. Canceling out the moles. And you're going to grams because it wants to know how many grams are in your, how many grams you'll theoretically get. Which, in this circumstance, is 2,076 grams, sorry. Grams of Fe2O3, Fe2O3, or if you need to convert it back to kilograms, which I would just put both answers down because it'll save you, possibly, it would be 2.076 kilograms of Fe2O3. And how I got that was that whenever you're doing significant figures, you go with the smallest amount of significant figures. So, a simple one is if you're doing 1.2 plus 3 plus 5 plus 5 point, hold on. If you're doing, say, 1.2 plus 3 plus 5.9999999, just repeating, equals, it would only be one digit. Because the 3 is one significant figure. So you only go to that one figure. Oh, shit. Hold on. Okay. Sorry about that. So what happens is you get that amount. Now, and that's your theoretical yield. That is your theoretical yield, your TY, as sometimes it's put. And real quickly, I'm going to do the other version, see how that works. Alright, so I just finished it, and that is your final amount, your theoretical yield. It's also right there. It's the same thing. It's 2,076 grams, or 2.076 kilograms. If I can just get this to focus, because I would hope you can zoom in a video. Just so that you can see it, but I really hope this helps.